Okay, lesson 5, here's your anti-set to start. So you should pause and just pause on this screen and try to complete the anti-set by yourself. And then when you unpause, it'll be me working through the answers. All right, so we'll start with sketching number 1. So we notice that this is a cosine-sine parametric, so this is going to be an ellipse. And it looks like the semi-major axis is going to be 3 and the semi-minor axis is going to be 1. And because the semi-major is on the y, this is going to be a more vertically elongated ellipse. So to sketch this, we don't have to do all these tick marks. We can just put some points down and then draw our ellipse. And we should label this as being 1, 0, 0, 3, negative 1, 0, and then 0, negative 3. So then we'll do number 2, 6 cosine t, 5 sine t. So again, let's draw our axes. So then we can do our points. And this is going to look kind of circular because the semi-major and the semi-minor are almost the same. So now we can connect our points here. And then I'm already forgetting, what do we got? X is 6, right? Okay, yeah, so we have, this is going to be 6, 0. This is going to be 0, 5. This is going to be negative 6, 0, 0, negative 5, right? We just know that we have a semi-major of 6, a semi-minor of 5, so we go 6, 6, 5, 5, and there is our sketch. It's not perfect, but it is labeled correctly, and that is all that really matters. So then, to determine which of these goes with which graph, we have to remember that secant represents the hypotenuse over the adjacent in a right triangle. And because the hypotenuse is always going to be longer than the adjacent side, the smallest this ratio could be is 1, but it could also be infinitely big. So secant goes from 1 to infinity, but tangent represents opposite over adjacent. And the opposite over adjacent ratio could be 0, and it could also be infinity. So when we think about these graphs, okay, this 3 secant then is going to go from 3 to infinity. And that's our x value, right? Our x value is going from 3 to infinity. So we're looking for the graph where our x value is going from 3 to infinity. And that is this one, because it starts at 3, 0, right? And that makes sense because tangent goes from 0 to infinity, right? So what's happening here is our x value starts as being 3, our y value starts as being 0, and then they both go off to infinity. X goes to infinity, y goes to infinity. So we can say then that this one goes here, and this one goes here. And because secant is now the y value goes from 3 to infinity, right? So we start at 0, 3. Okay, y value starts as being 3 and goes to infinity. The x value starts as being 0 and goes to infinity. So that's how we know that this is a hyperbola that opens up. What determines it is where secant is. If secant's x, then we open up horizontally. If secant's y, we open up vertically. Okay, so in this unit so far, we've come up with a different way of defining curves. We've done parametric. This means that x and y are both dependent on a third variable. It's often been time t. Now, in Cartesian form, we've always had y just being dependent on x. So in our curve, we only have x's and y's, whereas in parametric, we have x and y and then some kind of third variable. So this is the form we are used to, and the goal for this lesson is to convert a parametrically defined curve to a Cartesian form. Excuse me. So, to start, we're going to go back to the Pythagorean theorem, and it's not really clear why we would do that yet, but it will become clear as we work through this. So, quickly apply the Pythagorean theorem to this right triangle. If we do that, we get O squared plus A squared is going to be equal to the hypotenuse squared. The opposite side squared plus the adjacent side squared equals the hypotenuse squared. So now we're going to do a weird thing. we are going to divide by hypotenuse squared. We're going to divide by h squared. So divide each of these pieces by h squared. So if we divide this side by h squared, we have to divide this side by h squared. So what is that going to give us? Well, we get O over h squared. If we have O squared over h squared, O squared over h squared, that's the same as O over h squared, plus A over h squared equals h over h squared. But now what's this going to be? Well, these h's are just going to cancel, and this is just going to be 1. So we have O over h squared plus A over h squared equals 1. But now let's go back to trig. What is the ratio over h? Well, over h, opposite of our hypotenuse, is just sine. Let's go back to so, ka, toa. Sine is opposite of our hypotenuse, so we can replace over h with sine, sine squared. We can replace a over h with cosine, cosine squared, and that's equal to 1. So we call this a Pythagorean trig identity. A Pythagorean trig identity. Because we call it an identity because sine squared plus cosine squared has an identity of 1. Anytime we see sine squared plus cosine squared in a mathematical expression, we can just replace it with 1. So what I want you to try now by yourself is we divided by h squared before. Divide by O squared instead and see what happens. Divide by A squared instead and see what happens. And that's going to give us 2 other Pythagorean trig identities. So if we divide everything by A squared, that's going to give us O squared over A squared plus 1 equals H squared over A squared. But over A is just tangent, that's TOA. And then h over a is secant, as we covered in Unit 7, right? It's the reciprocal of cosine. So we have tangent squared plus 1 equals secant squared. This is another Pythagorean trig identity. Anytime we see secant squared, we can replace it with tangent squared plus 1. We can use this to manipulate algebraically. So now let's divide by O squared. Divide everything by O squared. Okay, O squared over O squared is 1, and then we have A over O, and we have H over O. A over O is just the reciprocal of tangent, that's cotangent. And then H over O is the reciprocal of sine, so it's cosecant. So we have 1 plus cotangent squared equals cosecant squared. Here's all 3 of them side by side. And what I want to point out is they don't have to be in this order. We can always subtract sine. If we subtract sine squared from both sides, that's algebraically fine, and that just gives us cosine squared equals 1 minus sine squared. So anywhere we see a cosine squared, we could replace it with 1 minus sine squared in any kind of mathematical expression. Okay, we could subtract our 1 over and make this tangent squared equals secant squared minus 1. We could subtract our 1 over and say cotangent squared equals cosecant squared minus 1. The point is you can manipulate these depending on what kind of expression you're working with, but these are the baseline Pythagorean trig identities. So now we're going to see how to use these to convert. Remember, our initial goal was to convert a parametric form of an equation of a curve to Cartesian form. So we're going to start with this ellipse, 5 cosine t, 3 sine t. So our goal is to try to manipulate this so that we can somehow apply our Pythagorean trig identities. And the first thing I notice about my identities is there's a lot of squares going on, right? Sine squared, cosine squared. So what I want to do first is just square these. So we get x squared equals, squaring this gives me 5 squared and cosine squared. Squaring this gives me 9, 3 squared, and sine squared. So now I have x squared equals 25 cosine squared, y squared equals 9 sine squared. But then the next thing I notice in my Pythagorean trig identities is that there's no coefficient in front of my sine or cosine. It's just a coefficient of 1. So if I want to just get sine squared, cosine squared, I need to divide my 9 over, I need to divide my 25 over. So I divide by 25 on both sides, I divide by 9 on both sides. And now I have x squared over 25 equals cosine squared, y squared over 9 equals sine squared. Stop and think, how can we use those identities we just learned to combine these? Okay, well, so pause and think. Okay, are you unpaused? Let's see. Cosine squared plus sine squared is going to be 1. Cosine squared plus sine squared is going to be 1. So x squared over 25 plus y squared over 9 is going to be 1. So here is our Cartesian form of the ellipse that we defined as 5 cosine t, 3 sine t. Now this is how you learned ellipses last year. Let's mess with this for a sec. What if x equals 5? Well, then we have 5 squared over 25 plus, we're not sure what y squared is, equals 1. Okay, well we have 25 over 25 plus y squared over 9 equals 1. Oh, well this is just 1 plus y squared over 9 equals 1. So what does y have to be for this equation to be true? Y would have to be equal to 0. So we have a point, oops, undo. We have a point at 5, 0. Okay, well what if y equals 3, right? Well that means we're going to have x squared over 25 plus y squared, or sorry, 3 squared is what y is. So 3 squared over 9 equals 1. And well, you should see that this is just going to be 9 over 9, which is 1. So then x is going to have to be 0. So then we have a point at x equals 0, y equals 3. Okay? In the negative direction, it's going to be the exact same. We're going to have a point at -5, 0, and 0, -3. So now we can draw our ellipse. Okay, and that is exactly the same sketch you would have gotten if you had done the parametrically defined curve like we did in the antiset. So this is just another way of defining this ellipse. And this ellipse is only defined with 2 variables, x and y, versus x and y depending on a third variable. Okay, we're going to do one more, and then I'm going to split it up and take a break and make another video. So try this one, convert the parametric equation to a single Cartesian function. So you should pause and try, and then unpause and check the answer. So we square both sides. X squared equals 9 cosine squared t, and then divide the 9 over. Square both sides, divide 36 over. And then our Pythagorean trig identity says we can add these together and set them equal to 1. So x squared over 9 plus y squared over 36 equals 1. Okay, when x equals 3, y is going to have to be 0. When y equals 6, x is going to have to be 0, because this would give us 3 squared over 9, which is 1, which means this piece has to be 0. Or it's going to give us 6 squared over 36, which is going to be 1. And then this piece has to be 0. So we have points at, well, 3, 0. And then at 0, 6, right? And then obviously we'd have similar points, mirrored points down there, and then we can draw our ellipse, right? Okay, which is the same ellipse we would have gotten if we had just sketched the parametrically defined one, 3 cosine t, 6 sine t, still have a semi-major axis of 6 and a semi-minor axis of 3. Okay, so we're going to talk about hyperbola now, but that will be in the next video. So you can take a break before then.